Okay, so let's say that we have these two parametric equations here. X is equal to t squared minus 1 and y is equal to t cubed plus t squared. And let's say that we need to find dy over dx. So the way that we're going to do this is firstly we're going to differentiate both of these parametric equations here. So if we differentiate this one, it will be dx over dt. And if we differentiate this one, it will be dy over dt. And then we can use this formula here in order to find dy over dx. So dy over dx is equal to dy over dt divided by dx over dt. The way that I remember this is to think about it like fraction. So if we have this dy over dt divided by dx over dt, remember when you divide by a fraction, it flips it. So dividing by dx over dt is the same as multiplying by the flipped fraction dt over dx. And then this dt will cancel out with this dt to just leave us with dy over dx. This isn't mathematically how it works, but I think at A level, and this is the way that I remember it, it's fine to think about it like this. So if we look at this particular example, so if we first differentiate this here to get dx over dt, so it's going to be t squared differentiated, which is going to be 2t, and then minus 1 is just a constant, so that would just go away when differentiated. And then if we differentiate this here to get dy over dt, it's going to be t cubed differentiated, which is 3t squared, and then t squared differentiated, which is 2t. And then dy over dx is going to be dy over dt divided by dx over dt. So it's going to be 3t squared plus 2t divided by 2t, like this here. When we have this two terms in the numerator and one term in the denominator, we can split up the fraction like this here. So we have 3t squared over 2t, and this t will cancel out one of the t's up here and leave us with 3 over 2t. Then this 2t will cancel out with this 2t to just leave us with 1 here. So dy over dx is equal to 3 over 2t plus 1. Okay, so here's another example question where we're told that a curve is defined by the parametric equations x is equal to t e to the power of t and y is equal to sin of 2t, and we need to find dy over dx. So we're going to use the same equation as before, that dy over dx is equal to dy over dt divided by dx over dt. So if we start with dy over dt, so we need to differentiate this here. So remember how to differentiate this here. Firstly, when you differentiate sin, it becomes cos, but also remember that when you have a 2 in the trigonometric function here, it comes to the front as a coefficient. So when we differentiate this, it's going to become 2 cos of 2t. So that's dy over dt. And then dx over dt is going to be this differentiated. Now here we have two terms multiplied together, the t and the e to the power of t. So this is a sign that we need to use the product rule. So we did a video on the product rule in this chapter already, so go back to that if you need a reminder. But essentially how the product rule works is you differentiate this term here and then multiply it by this term, and then you differentiate this term here and multiply it by this term. So therefore dx over dt is going to be t differentiated, which is 1 multiplied by e to the power of t, and then e to the power of t differentiated, which is still just e to the power of t multiplied by t, like this here. 1 times e to the power of t is just e to the power of t, and then e to the power of t multiplied by t is t e to the power of t. So that's dx over dt. So therefore dy over dt divided by dx over dt is equal to 2 cos 2t divided by e to the power of t plus t e to the power of t. So that's dy over dx. Okay, so here's another example question where we're told that curve C is defined by the parametric equations x is equal to the natural log of t minus 1 and y is equal to t squared minus 2t plus 2. And we need to find the gradient of the curve when t is equal to 5. Now remember, the gradient is just dy over dx. We essentially just need to find dy over dx when t is equal to 5. So we're going to use the same method as before. So dy over dx is equal to dy over dt divided by dx over dt. So if we start with finding dy over dt, so we're going to differentiate this parametric equation here. So if we differentiate t squared, this is going to be 2t, and if you differentiate minus 2t, this is going to be minus 2, and if you differentiate plus 2, as it's just a constant, it goes away. So dy over dt is equal to 2t minus 2, and then if we find dx over dt. So this is going to be the x parametric equation differentiated. If you differentiate the natural log of t, we've talked about in the differentiation chapter how we differentiate natural logs. It's going to be 1 over t, and then minus 1 again is a constant, so it just goes away. So dx over dt is equal to 1 over t. So dy over dx is equal to dy over dt divided by dx over dt. So this is going to be 2t minus 2 divided by 1 over t. Now remember, when you divide by a fraction like this, it flips. So dividing by 1 over t is the same as multiplying by t. So dy over dx is going to be t, and then this 2t minus 2. And then we're just going to sub in t is equal to 5, which is going to look like this here. 2 times 5 is 10, minus 2 is 8, so this is going to be 5 times 8, which is 40. So dy over dx is equal to 40. Okay, so now let's go through some past exam questions. So for this one here, we're told about a curve C that has the parametric equations x is equal to sin 2 theta and y is equal to cosec cubed theta, and theta is between 0 and pi over 2. And for part A, we need to find an expression for dy over dx in terms of theta. Now for this particular question, there's no t, kind of the role of t has been taken over by theta here. So we're going to use the same method as before though to find dy over dx, just in terms of theta this time. So dy over dx is equal to dy over d theta divided by dx over d theta. So to find dy over dx, we first need to find dy over d theta and dx over d theta. So if we start with dy over d theta, so we need to differentiate this parametric equation here. Now to differentiate cosec cubed theta, it might be easier to see this if we write this as y is equal to bracket cosec theta to the power of 3. So to differentiate this, we need to use the chain rule. Now I did a video on the chain rule in the differentiation chapter, and there's loads of ways that people teach the chain rule, but the way that I taught it is that the chain rule is the inner function differentiated multiplied by the outer function differentiated, where for this example here, cosec theta to the power of 3, the inner function is cosec theta and the outer function is this power of 3 here. Okay, so in order to differentiate this, it's going to be the inner function differentiated, so it's going to be this cosec theta differentiated, and this is one of the standard integrals that's in the formula booklet. When you differentiate cosec theta is equal to minus cosec theta cot theta, and then this is multiplied by the outer function differentiated, so this is this power of 3 differentiated. Think about this like x to the power of 3. When you differentiate this, it's equal to 3x squared. So this power of 3 comes down as the coefficient like this here. We don't touch the cosec theta here. This is kind of like the x. We kind of ignore it. And now it's going to be to the power of 2 instead. So this is the outer function differentiated. And therefore this is dy over d theta. And we can simplify this because we have this minus here multiplied by this 3. So it's going to be minus 3 at the front here. And then we have this cosec theta multiplied by this cosec theta to the power of 2. So this is going to be cosec theta to the power of 3. So dy over d theta is equal to minus 3 cosec cubed theta cot theta. Okay, so we found dy over d theta, so now we need to find dx over d theta, so we need to differentiate this here, and this we've actually already covered in this video, this sin 2 theta. When we differentiate sin, it becomes cos, and then we move this 2 to the front here. So dx over d theta is equal to 2 cos 2 theta. So therefore dy over dx is going to be dy over d theta, so this is this minus 3 cosec cubed theta cot theta, divided by dx over d theta, which is this 2 cos 2 theta. So this here is dy over dx. Okay, and then for part B, we need to find the exact value of the gradient of the tangent to C at the point where y is equal to a. So what this question is asking us is to find the gradient. Remember, the gradient is dy over dx. We need to find dy over dx when y is equal to 8. Okay, so the way that we need to do this is we need to find dy over dx for this particular coordinate y is equal to 8. Now we're going to need the theta value for this because we have a dy over dx equation in terms of theta. So the way that we're going to do this is y is equal to 8, and we have this parametric equation for y here. So what we're going to do is we're going to sub in y is equal to 8 into this. So we're going to say that 8 is equal to cosec theta to the power of 3, like this here, and then rearrange in order to find theta. If we cube root both sides, we get that 2 is equal to cosec theta. Remember, cosec theta is equal to 1 over sin theta, so that means that 2 is equal to 1 over sin theta. And if we bring this kind of 1 numerator onto this side, we get that a half is equal to sin theta. So therefore, that means that theta is going to be equal to pi over 6 if you put it into your calculator. So theta is equal to pi over 6, so that means what we're just going to do is sub in theta is equal to pi over 6 into this equation here. So it's going to be minus 3, and then this cosec to the power of 3 theta. You could sub in theta here, but we know that cosec to the power of 3 theta is equal to 8. So I've just replaced this cosec to the power of 3 theta with 8 here, and then cot of theta, so cot of pi over 6 over 2 cos 2 of this pi over 6 in. If you put this into your calculator, you get out a value of minus 24 root 3. So this is the answer. This is the value of the gradient at the point where y is equal to 8. Okay, so here's another exam question. So we're told a curve C has parametric equations x is equal to 2 cos t and y is equal to root 3 cos of 2t. And for part A, we need to find an expression for dx. So this is the same equation as normal. dy over dx is equal to dy over dt divided by dx over dt. So if we first focus on finding dy over dt by differentiating this here, so it's going to be this root 3 here multiplied by cos 2t differentiated. When you differentiate cos 2t, so when you differentiate cos, you get minus sin, but remember you have this 2 here that's going to go to the front, so it's going to be minus 2 sin 2t like this here, then minus 2 times root 3 is minus 2 root 3, and then this sin 2t. So that's dy over dt, and then to get dx over dt, we're going to differentiate this here, so it's going to be 2 multiplied by cos t differentiated, which is minus sin t. Remember the minus, so therefore it's going to be minus 2 sin t. So that's what dx over dt is equal to. So therefore dy over dx is going to be dy over dt divided by dx over dt. So it's going to be this minus 2 root 3 sin 2t over minus 2 sin t. We can do some simplifying on this because this minus 2 can cancel out with this minus 2 to leave us with root 3 sin 2t over sin t. We can do some more simplifying here because remember we have this sin 2t at the top here. Remember the double angle formula that sin 2t is equal to 2 sin t cos t. So therefore we can write this as 2 root 3 sin t cos t, then this sin t can cancel out with this sin t to leave us with 2 root 3 cos t. So dy over dx is equal to 2 root 3 cos t. Okay, so for part B, we're told about a point P that lies on the curve where t is equal to 2 pi over 3. And we're told about a line L that is normal to C at P. And we need to show an equation for this line L, which is the normal, is equal to this here. So let's just draw a quick diagram to what's going on. So we have this curve and we have points, which is P, we'll say it's this here. And remember what a normal is. A normal is perpendicular to the curve. So the normal is going to be like this here, where this is a 90-degree angle. And we need to find an equation for this normal. Now remember, normal is a straight line, so we need to find the equation of a straight line. So we're going to use this equation that we talked about back in year 1, chapter 5, where it's y minus y1 is equal to mx minus x1. In order to find the equation of a straight line, you need two things. You need the gradient of this line, the gradient of the normal, and you also need a coordinate. You need a point on this line. Okay, so let's start with the gradient because this is easy. Remember, the gradient is dy over dx, and we have an equation for dy over dx, and we're told that the normal is at the point P, and we're told that at the point P, t is equal to 2 pi over 3. So what we can just do is sub in 2 pi over 3 into this dy over dx equation like this here, and if you put this into your calculator, you get that dy over dx is equal to minus root 3. So this is the gradient at the point P on the curve C. However, this is not what we're looking for because remember the normal is perpendicular to the curve. And if you remember how perpendicular gradients work, if you have a gradient m, if you have a perpendicular line, its gradient is going to be the negative reciprocal of that gradient. So it's going to be minus 1 over m. So therefore, if the gradient on the curve is minus root 3, the negative reciprocal of minus root 3 is going to be positive 1 over root 3. So this here is the gradient of the normal because it's perpendicular to the curve. So we have the gradient, now we need a coordinate on the normal, and we're told that the normal is at point P. So that means a point on the normal is this point P. So therefore what we can do, as we're told that the point P lies on the curve where t is equal to 2 pi over 3, we can just use these parametric equations up here in order to sub t is equal to 2 pi over 3 into them in order to find out what the x and y coordinate are at this point, and then we can use this coordinate on the normal. So therefore that's what I've done down here. So x is equal to 2 cos t, and I've subbed in 2 pi over 3. If you put this into a calculator, this is equal to minus 1, and then y is equal to root 3 cos of 2 of this t, which is 2 pi over 3, which if you put into your calculator is equal to minus root 3 over 2. So therefore a point on the normal, this point P here, is minus 1 minus root 3 over 2. So therefore we can use this equation here for the straight line. So it's going to be y minus y1. So remember, y1 is the y coordinate of this point, so it's this minus root 3 over 2, so it's minus y1, so it's going to be minus root 3 over 2, so it's going to be plus root 3 over 2 is equal to m, which is the gradient, which is this 1 over root 3, and then x minus x1, so x1 is this minus 1 here, so it's going to be minus 1, so it's going to be plus 1. So this here is the equation of the straight line, and we need to show that it can be written in this format here. So firstly, we have this root 3 in the denominator here of this fraction, which is quite untidy. So what we're going to do here is multiply everything in this equation through by root 3, so it cancels out this denominator here. So if we do this, this y will become root 3y. If you multiply root 3 over 2 by root 3, this root 3 times root 3 will be 3, so this will become 3 over 2, and then this 1 over root 3 will cancel out and go away, so we're just left with this x plus 1 here, okay? If we move this stuff, this root 3y plus 3 over 2 onto this side, because we need it to be equal to 0, we get that it's minus root 3y plus x minus a half is equal to 0. You can see that this is the exact equation we've got here, but everything here is multiplied by 2. You can see we've got x here, they've got 2x, we've got minus root 3 here, they've got minus 2 root 3, and they've got minus 1 here, we've got minus a half. So if we just multiply through by 2, we get that minus 2 root 3y plus 2x minus 1 is equal to 0, which is the equation that they want. Okay, so for part C, we're told that the line L intersects the curve C again at the point Q, and we need to find the exact coordinates of Q. So let's draw our diagram here, again, to show what's going on. So we have this curve here, C, that has this parametric equations here, and as we talked about before, we have the point P that L is the normal to, so it's 90 degrees to, and we're told that this line L intersects at another point on the curve, which is Q, and we need to find the coordinates of this. So this is essentially a points of intersection question, and we talked about points of intersection questions in regards to parametric equations back in year 2 of chapter 8 in the parametric equations video. So I'd recommend going back to that, but the way that we're going to tackle this is that this is a points of intersection question between the line L, which has this equation here that we figured out in part B, and the curve C that has these parametric equations here. So what we're going to do is, for the equation of line L, we have these y and x terms here, and for the parametric equations, y and x are the subjects here. So what we're going to do is we're going to substitute out the y here for this root 3 cos of 2t, and we're going to sub out the x here for this 2 cos t. So the equation is going to become this. So it's minus 2 root 3, but instead of y here, it's now this root 3 cos of 2t plus 2, and then instead of x here, it's now this 2 cos t minus 1 is equal to 0. And what we're going to do is we're going to rearrange in order to find the value of t, and this value of t is going to be the value of t for this point Q, and then we can use that in order to find the coordinates of Q, okay? So we need to rearrange this in order to find the value of t. So if we do this, so firstly we have this minus 2 root 3 multiplied by root 3. Root 3 times root 3 is 3, and then 2 times root 3 is 6. This is going to be minus 6 cos 2t. And then here, 2 times 2 is 4, so this is going to be 4 cos t, and then minus 1 is equal to 0. Now here we have this cos 2t, so this is a sign that we can use the double angle formula. Now remember, for cos 2t, there are two versions of the double angle formula. There's the sin version that produces sin squared t, and there's the cos version that produces cos squared t. So which one of these are we going to use? So we talked about how to solve equations like this back in year 2 of chapter 7 in the trigonometric identities and equations video. One of the things we talked about is, so this is going to become a trigonometric quadratic, because whatever we sub in, it's either going to be sin t squared, so squared it's a quadratic, or cos squared t, so it's going to be a square. So it's going to become a trigonometric quadratic. One thing we talked about with trigonometric quadratics is when we're solving the equations, we only want one trigonometric function present. So what I mean by that is we either only want sin present or we only want cos present. We don't want an equation that has both sin and cos present. It becomes a bit confusing. And you can see here we have this cos t present, so therefore this shows that we don't want to use the sin version here. We want to sub in the cos squared t version, so therefore we're left with an equation that only involves cos. Okay, so the double angle formula for cos 2t for cos is 2 cos squared t minus 1, like this is. So if we sub this in for cos 2t, it's going to become minus 6, and then instead of cos 2t, it's this 2 cos squared t minus 1 plus 4 cos t minus 1 is equal to 0. And now we have an equation here that only involves cos, so therefore we can go about solving this. So firstly, let's expand this bracket here. So minus 6 times 2 is minus 12, so it's going to be minus 12 cos squared t, and then minus 6 times minus 1 is plus 6, like this here, plus 4 cos t minus 1 is equal to 0, plus 6 minus 1 is plus 5. So we've got this equation here, minus 12 cos squared t plus 4 cos t plus 5 is equal to 0. And this is a quadratic. Now we know loads of ways to solve quadratics. I'm just going to use the quadratic formula where, so remember the quadratic formula, this here is a, this minus 12, this here is b, and this here is c. So the quadratic formula is minus b plus or minus the square root of b squared minus 4ac over 2a. So if you plug in these a, b and c values, you get this here. So therefore cos t is equal to this, which if you put this into your calculator, you get out a value of either 5 over 6 or minus a half. So we've solved this quadratic. Cos t is equal to either 5 over 6 or minus a half. Okay, so we get that cos t is equal to minus a half or 5 over 6. So which one of these is it, okay? Well, if you find t by taking the inverse cos of minus a half and 5 over 6, you get that t is equal to either 2 pi over 3 for the minus a half, or t is equal to 0.585 for the 5 over 6. If you look at the question, we're told that the point P lies on C, where t is equal to 2 pi over 3. So this is this t value here. Now remember, P is this here. It's the point at which L is normal. This is not the point that we're looking for. We're looking for the point here, Q, where it intersects the curve again. So therefore it's not this value here. It's going to be this t value, where t is equal to 0.585. Okay, so now we just need to use this t value in order to sub them into these parametric equations here in order to get the values of x and y and get the coordinates of q. Now we have one problem with this. If we use this t is equal to 0.585, as it wants the exact coordinates of q, if you try and sub this t is equal to 0.585 into these x and y parametric equations here, like this, you get out values for x is 1.67 and y is 0.68. These are not the exact coordinates of q. These are decimal values. These are rounded decimals. The reason that these are not the exact coordinates is that this is not the exact value of t, because this is also a rounded decimal. Okay, so in order to get out the exact values of x and y, what we have to do is not use this t value here that gives out these non-exact coordinates. We need to use the fact that cos t is equal to 5 over 6, because this is an exact value. Cos t is equal to 5 over 6. Okay, this is a fraction. Okay, so what we're going to do here is, if we start with the x parametric equation, because this is easier, it's going to be x is equal to 2, but here we have cos t, so rather than cos t, we're just going going to sub in this 5 over 6. 2 times 5 over 6 is 5 over 3. So x is equal to 5 over 3. This is the exact value. Now, if we look at the y parametric equation, we have y is equal to root 3 cos of 2t. So this cos 2t, if we use a double angle formula for cos 2t that involves cos, so this 2 cos squared t minus 1, we can sub this in and get that y is equal to root 3, but instead of this cos 2t here, it's this 2 cos squared t minus 1. And this cos t here, we can sub in this 5 over 6. So it becomes root 3, and then this 2, and then instead of this cos t, it's this 5 over 6. It's squared, remember, because this is cos t squared minus 1. If you put this into a calculator, you get out that y is equal to 7 root 3 over 18. So these are the exact values of x and y. You have to do it using this method rather than doing this one where you only get out the approximate values. So therefore the exact coordinates of q are 5 over 3, 7 root 3 over 18. Okay, so here's one final exam question for this video. This is a really long question, so I've tried to show it as best as I can on the screen here with all of the parts, and then when we're going through the individual part A, part B and part C, I'll enlarge those parts, but here's the entire question. Okay, so for this question, we're given this sketch here, and we're told it's of the curve C with parametric equations. X is equal to 2 tan t plus 1, and y is equal to 2 sec t squared plus 3. And we're also given this domain here between minus pi over 4 and pi over 3. And we're told that the line L is the normal to C at the point P where t is equal to pi over 4. So we can see this on the graph. So this is the curve here with the parametric equations here, and the line L is the normal at this point P, so remember it's 90 degrees to the curve. And for part A, we need to use parametric differentiation to show that an equation for L is this here. So remember that L is a straight line, and to get an equation for a straight line you need two things. You need a point on the line, you need the coordinates of the point on a line, and you need the gradient. So let's first focus on the gradient. So we can get the gradient because we can figure out the gradient of the curve at this point P, which we'll call M, and then remember, because the normal is perpendicular to the curve at this point, the gradient is going to be the negative reciprocal of the gradient of the curve. And we can figure out the gradient of the curve here by finding dy over dx, and it tells us this in the question by using parametric differentiation. So dy over dx is equal to dy over dt divided by dx over dt. So we need to differentiate these equations here. So if we start with this one here, the y, so it's going to be dy over dt is equal to 2 multiplied by, and then we're going to differentiate this sec squared t. Now for this we need to use the chain rule. It might be a bit more obvious if we write it as brackets sec t squared like this here, where the inner function is sec t and the outer function is the power of 2, and the chain rule is the inner function differentiated multiplied by the outer function differentiated. If we differentiate the inner function, which is this sec t, remember when you differentiate sec t, it's sec t tan t. When you differentiate sec, it's sec tan. And then this is multiplied by the outer function differentiated, which is this power of 2 differentiated. Remember, when you differentiate a power of 2, the 2 comes down as the coefficient. Remember, we don't touch the inner function, we just keep this as the sec t, and now it's going to be to the power of 1. And then we can simplify this because 2 times 2 is 4, and sec t multiplied by sec t is sec t squared here. So dy over dt is equal to 4 sec squared t tan t, and we have this plus 3 here as well, which when you differentiate a constant, remember, it just goes away. So therefore dy over dt is just equal to this, and then we need to differentiate this here, so this is going to be dx over dt is equal to, and then it's going to be this 2 tan t, so it's going to be 2, and then when you differentiate tan, remember, you get sec squared, so dx over dt is equal to 2 sec squared t. Again, this plus 1, when you differentiate a constant, it just goes away. So therefore dy over dx is equal to dy over dt divided by dx over dt. So this is 4 sec squared t tan tan t divided by 2 sec squared t. We can do some simplifying here because this sec squared t will cancel out with this sec squared t, and this 4 and 2 will cancel down to just leave us with a 2 here. So dy over dx is going to be equal to 2 tan t. Okay, so we have dy over dx is 2 tan t, so now we're going to find the gradient of the curve at this point P, where t is equal to pi over 4. So all we're just going to do is sub in pi over 4 as t into dy over dx. So it's going to be 2 tan of pi over 4, which if you put into a calculator is equal to 2. So this is the gradient of the curve at P. Now we want the gradient of the normal at P, so this is going to be the negative reciprocal of this gradient here too, so therefore this gradient of the line is going to be minus 1 over 2 like this here. So this is the gradient of the line. So now we just need a point on the line, and this is easy because we're told this is where t is equal to pi over 4, so therefore we can just sub this into these two parametric equations here in order to get our x and y. So that's what I've done here. I've subbed in t is equal to pi over 4, so for y it's 2 sec squared of pi over 4 plus 3, which if you put into a calculator is equal to 7, and x is equal to 2 tan of pi over 4 plus 1, which if you put into a calculator is equal to 3. So the point P, one of the points on this normal here, is 3, 7. So therefore, if you use the equation of a straight line that y minus y1 is equal to mx minus x1, we can get that y minus, so this y coordinate here is 7, is equal to the gradient, which is minus a half of x minus 3, which is this x coordinate here. We can expand this bracket here using this minus a half, so it becomes minus a half x plus 3 over 2, and then bring this minus 7 onto this side, so it becomes y is equal to minus a half x plus 17 over 2, which is what's required. Okay, and then for part B, we need to show that all the points on the curve C satisfy this equation here. And this is the type of question that we talked about a lot back in the parametric equations chapter. Essentially what this question is just asking us is to convert these parametric equations into this Cartesian equation here, which we know how to do. Now, if we look at these parametric equations here, we can see that we have a tan here, and we have a sec here, and specifically we have a sec squared here, which is quite interesting because that means that one thing that could be useful to us is the trigonometric identity that 1 plus tan squared t is equivalent to sec squared t, and we can sub this tan t in and this sec squared t in. Okay, so let's first focus on this y parametric equation here. So this plus 3, if we move this to the other side, we get that y minus 3 is equal to 2 sec squared t, and then if we divide both sides by 2, we get that y minus 3 over 2 is equal to sec squared t. So what that means is for this sec squared t here, we can sub in this y minus 3 over 2, so that's good. And then if we look at the x parametric equation, so we have this tan here, so this plus 1, if we move this to the other side, we get that x minus 1 is equal to 2 tan t, and to divide both sides by 2, so we get that x minus 1 over 2 is equal to tan t, okay? Now be careful because this is a tan t to the power of 2 here, so if we're going to sub this in, we need to raise this here to the power of 2. But therefore we can sub in this y function here and this x function here like this, so therefore we can rewrite this as 1 plus, and then instead of this tan squared t here, we can write this as x minus 1 over 2 squared. Remember, this thing here needs to be squared, so it's to this power of 2 here, and this is equal to sec squared t, which we can sub in here as this y minus 3 over 2 like this here. We don't need the squared here because this is already equal to sec squared t like this. Okay, so we need to get it into this format here, so let's do some simplifying. So firstly, you can see that we have this x minus 1 squared in our final answer, which we have this x minus 1 squared here. So let's not expand that, let's just leave it like that. This 2 here in the denominator, this is to the power of 2. So if we do this, so 2 squared, this is equal to 4. So it's 1 plus x minus 1 squared over 4 is equal to y minus 3 over 2. Let's get rid of the 4 in the denominator, so let's multiply everything through in this equation by 4. So this 1 will become a 4, and then it's going to be 4 plus, and then this 4 here will cancel out to leave us with x minus 1 squared, like this here. This 2 will cancel out and leave us with times 2 here, so it's going to be 2y minus 6. Move this minus 6 to the other side, so we get the x minus 1 squared plus 10 is equal to 2y, and then divide both sides by 2y, so we get that y is equal to half x minus 1 squared plus 5, which is what's required. Okay, so for part C, we're told about a straight line with equation y is equal to minus a half x plus k, and we're told this line intersects C at 2 distinct points, and we need to find the range of possible values for k. So let's draw on this diagram here what's going on here. Ignore line L, this isn't relevant for part C. So this line here is in the form y is equal to mx plus c, where m, the gradient, is minus a half, and c, which is the y-intercept, is k. So this line is going to look something like this here, where the y-intercept of this line is k, and it intersects this curve C at 2 distinct points. Now we need to find the range of possible values for k, because of course there is more than one line that could do this. For example, the line could be down here instead, and it still intersects at 2 distinct points, or the line could be here and it still intersects at 2 distinct points. So we need to find the range of values of k for which this happens. Now, as we're dealing with points of intersection between this line here and the curve C, which we figured out in part B has this equation here, what we're going to do, because they're both equal to y, we're going to equal these two equations to each other. So what we're going to say is that minus a half x plus k is equal to this half x minus 1 squared plus 5. Remember, because this is how we deal with points of intersection, and now we have an equation that only involves x. Okay, so let's simplify this. Okay, so we have this x minus 1 to the power of 2, which if we expand this is equal to x squared minus 2x plus 1, and then we can expand this because we have this half in front of this whole bracket here, so this is going to be half x squared minus x plus a half, and then a half plus 5 is equal to 11 over 2. And then if we bring this minus a half x plus k onto this side in order to equal this equation to 0 and make it a quadratic equation, so this would become, so this would still be half x squared because there are no x squared terms on this side. This minus a half will go onto this side to become plus a half x, so it's going to be minus x plus a half x, which is going to be equal to minus a half x, and then this k is going to go onto this side, so it's now going to be minus k, like this here. As we have these two denominators everywhere, just to simplify, we're going to multiply this whole equation through by 2, so this becomes x squared minus x plus 11, and now it's going to be minus 2k, and this is equal to 0. Okay, so we have this quadratic here, and now we need to use the information that this line and this curve intersect at 2 distinct points. Okay, so if there are 2 points of intersection, that means that for this quadratic the discriminant is going to be bigger than 0. Go back to the videos that we made on the discriminant. But if you have 2 points of intersection, this quadratic, the discriminant is going to be bigger than 0. If, for example, the line had 1 point of intersection instead, like this here, the discriminant would be equal to 0. And if the line had no points of intersection, like let's say it was down here, the discriminant would be less than 0. But as the line intersects twice, therefore the discriminant is going to be bigger than 0. And b squared minus 4ac, where b is this coefficient here, this minus 1, a is this coefficient here, so this 1, and c is this 11 minus 2k. So we can sub it in like this here. And what's useful about this is we can rearrange this in order to get an inequality for k, and this will give us the range of possible values for k. Okay, so if we simplify this, so minus 1 squared is 1, and then minus 4, this is just times 1, so we can just ignore this. Minus 4 times 11 is equal to minus 44, and minus 4 times minus 2k is equal to plus 8k, like this here. 1 minus 44 is equal to minus 43, it says minus 43 plus 8k is bigger than 0. Move this minus 43 to the other side of the inequality, so we get that 8k is bigger than 43, and divide both sides by 8, so we get that k is bigger than 43 over 8. So this means that this is the inequality for which there are 2 points of intersection when k is bigger than 43 over 8. Okay, so what does this k bigger than 43 over 8 mean graphically? Okay, so I've drawn the line here where k is equal to 43 over 8. So remember, k is the y-intercept. So here k is equal to 43 over 8, and here there is 1 point of intersection here. This line is essentially a tangent to the curve C. So this is why it is not k is bigger than or equal to 43 over 8, because when it's equal to 43 over 8 there is only 1 point of intersection. However, anything bigger than 43 over 8, so for example if you draw it like this, here there are 2 points of intersection, so that's where this inequality comes from. Now, normally this would be the final answer if this was a normal curve. However, because this is defined with parametric equations and with this domain here, there is one other detail you need to realise in order to give all 5 marks. If this domain wasn't here, then this curve would keep going for all values of x. So on this side it would keep going up like this, and on this side it would keep going up like this. So for example, let's say that we had the line here like this, so we can see that this has 2 points of intersection. However, because of this domain here, we do not cover all x values, and the curve doesn't go up to these points here. The curve only goes up to here and here. So what this means is this line actually only has 1 point of intersection. This side is not a point of intersection. So what this means is there is also an upper value for k as well, for which there are 2 points of intersection. So what is this upper value of k going to be? Okay, well, the biggest value that k can have is for this line here, where it has 2 points of intersection. Anything bigger than this, so like this for example, you still have the point of intersection here, but you don't have the point of intersection here. So this line here that I just drew is the biggest value that k can have. This is kind of the highest that the line can be. So what is the k value for this line? Okay, so if we look at this point here, we can see that this is kind of the leftmost point. This is the smallest x value, and this is going to be the smallest value in the domain. So the domain here, the smallest value of t is this minus pi over 4. It can also be equal to this as well. So therefore, in order to find this point here, this will be for this t value here. This t is equal to minus pi over 4. So if we sub this into the parametric equations for x and y, like this here, so x is equal to 2 tan of minus pi over 4 plus 1, which if you put into your calculator is equal to minus 1, and y is equal to 2 sec squared of minus pi over 4 plus 3, which if you put into your calculator is equal to 7. So that means that this point here is equal to minus 1, 7. So this point here is minus 1, 7. So what we're going to do is we're going to sub this point here into this equation in order to find the value of k for this line. So that's what I've done down here. So y is 7 and x is minus 1. We have this minus a half times minus 1, which is equal to a half, and bring this half to the other side. So we get that k is equal to 13 over 2. So for this line here, k is equal to 13 over 2. So as we said, anything bigger than k is equal to 13 over 2, there will no longer be 2 points of intersection, because here there won't be a point of intersection on this side. So therefore the upper value for k is it also has to be smaller than 13 over 2. It can also be equal to this point here as well, because it can intersect with this point here. So this here is the final answer. K has to be bigger than 43 over 8, but it has to be smaller than or equal to 13 over 2.